This is the MIE100 midterm from 2023. This is usually given at the beginning of March. Latest is roughly second week in March. And so we tend to cover, again, a very similar sort of set of materials with each year. And at this point, we have started rigid body kinematics. In this particular year, we had not gotten to acceleration. We had hit velocity, and so it covers all of the material up until rigid kinematics, body kinematics acceleration. It is always different dependent on the time of year because it depends on the material we've covered in lecture. One thing that starts to play a role in this is something that I've put in the syllabus for a number of years, which is the dynamic concept inventory. So I want to go back a little bit and talk about this. The dynamic concept inventory, why are we testing you on this, is a set of concepts that a number of instructors, I'm not part of this, I really like it. I think it's an extraordinary piece of work. But when it came down to it, and I read over all of this in the literature, and you can see the reference in blue at the very bottom right of the screen. It has a number of useful ideas, and I'm going to just read over them. Different points on a rigid body have different velocities and acceleration, which vary continuously. Angular velocities and accelerations are properties of the body as a whole, can vary with time. An object can have non-zero acceleration and zero velocity, non-zero velocity and no acceleration. The inertia of a body affects its acceleration. Particle has acceleration when it's moving with a relative velocity on a rotating object. So the idea in any effort to teach a first year course or an upper year engineering course is to know what exactly we're looking at. And these are sort of fundamental concepts that we tend to look at as we go through. Everything depends when the exam is offered. So we are looking at concepts that guide our testing and our teaching. So the first question was a small mass of mass equals 0.75 kilos is moving in a circular path on a table. And that circular path is shown here. It has a radius of r, string is attached, and the other end of the spring is a string is attached to a spring of stiffness k equals 50 newtons per meter. A force F of spring is applied. Ignore friction, the mass of the string, and the mass of the spring. Draw the free body diagram for the 0.75 kilo mass. So first things off, we really want you to know how to do free body diagrams. So at this point, you should be able to look at that and sort of say, okay, what do I have to have in there? Knowing that R equals 0.25 meters and F spring equals 45 newtons, do not vary with time. Find the magnitude of the angular momentum of the mass about the hole in the table. The force of the spring is slowly increased from 45 newtons until R is equal to 0.15 meters. So essentially, it shrinks it by 0.1 meter. So it goes in the second part to 0.15 meters here. What will be the final potential energy of the spring? So starting out, for a full sort of diagram, I need to know my tangential and normal directions, which are given. I need force of the string, which is the only force acting in the normal direction, and weight and normal force, which are acting up and down. There's no friction in this problem. Force of the string is equal to 45 newtons. It's mass times acceleration newtons in mv squared divided by rho. So normal acceleration. So I'm given 45 newtons. I put the terms in. I get v squared over here, and I get a final velocity of 3.87 meters per second. Don't have to go to 3 digits. For the angular momentum, I have also the magnitude of that, which is mvr, which is 0.75 kilos, and 3.87 meters per second, and 0.25 meters. And you were asked for the magnitude, so it's 0.726 kilogram meters squared per second. So if we say that we have the initial position 1 and the final position 2, and there are no external moments applied, then we have H1 equals H2. The two masses cancel because they're the same. And so we can get rid of that term from our expression. And we then have V1 to R1 equals V2 to R2. So we know that the initial R is 0.25 meters, final to R is 0.15, 3.87. Only unknown is this, which is 6.48 meters per second, 6 meters per second. Force times distance is a moment, and that moment is equal to mv2, quantity squared, and then we sort of put out the terms and get force of the spring, which is 208.3 newtons. So final force in the spring is that. Calculate that in terms of the spring constant and all the rest of the term. We have K, we have force of the spring, we have all of the terms that we need to sort of solve through for this. So we can substitute x squared with F over K, which is just a spring extension, and we end up with U equals to 434 joules. This last one was a bit conceptually, or second one was conceptually difficult. And what we were doing here is we had two masses on a belt. And you were given that for the first part, static coefficient, or both boxes, static coefficient was 0.4, mass of the block B was 16 kilos, mu KB equals 0.38, mu KA equals 0.32, MA equals 20 kilograms. Both blocks are on a stationary conveyor belt inclined at 15 degrees. You're given all that in the figure. Block moves up, or belt moves upward, causing the boxes to move with it. Mu sub s is equal to 0.4 for all contact. The coefficients are different for A and B. Mu Ka is 0.32 and mu Kb is 0.38. Determine the maximum acceleration of the boxes if they move together without slipping. So acceleration B equals acceleration of A, everything's moving with the same thing, and mu sub s is equal to 0.4 because there's no slip, and we assume that it's impending slip, which is that second condition that we consider where force of friction is equal to mu sub s n. Solving through for all of the terms, we do have our free body diagram. Again, remember, free body diagrams matter. Weight gets down, we have the normal forces acting normal to the belt, we have the two friction forces. Put in all the terms, you have the acceleration on the other side. Substitute and move things around a little bit. So I cheated a little bit, or no, I haven't cheated yet, but I have all the terms there. Substitute in all the expressions. We have mu sub s, which is mag cos theta, mu sub s mbg cos theta, mb and ma, and just recognize that this is na and this is nb. Substituting all the terms, keeping to a consistent coordinate system, everything is good. So everything can be sort of worked out very nicely because, bang, all of the mass terms disappear. So acceleration is minus g sine theta plus mu sub s g cos theta, and you end up with 1.25 meters per second squared. If the boxes slip and stay attached to each other, determine the accelerations of the boxes and the normal forces between the boxes. So if they remain in contact, you have a normal force from A on B and a B on A. And so those are shown in blue. And that's the only change that occurs really to this diagram. The force of frictions are now sort of separated because both of them are sort of moving, but you got to consider the normal force between the two. We know as the box remain in contact with the belt, normal A equals mag cos theta, NB mgb cos theta. Substituting in all the terms, you have two expressions that you're going to be looking at. One, which is the normal force in one, the normal force in the other. You have the two directions. You substitute them in, put everything together, calculate the same thing. You end up with a messy sort of expression where you can't quite do as nice a job because now this term down here, this term right here is not the same because the mu k's are not the same. So you can't get rid of that term. But you can sort of simplify things over here because you have MB times g sine theta over ma plus mb, so that term just becomes sine theta. The rest of it is still there. It's a little bit of calculator work, but nothing too terrible. Using the A calculated in either expression, you can get the normal force between the two normal AB. And if you didn't have to do that, you wouldn't have to solve, or you wouldn't have to work. But there you go. If the boxes slip and separate, determine the accelerations of the two boxes. Again, both boxes stay in contact with the belt. If they separate, then the normal force between the two is 0, and acceleration A does not equal acceleration B. So I've drawn in the free body diagram with a dashed arrow to indicate a normal force of 0 at both of those terms. And the normal forces are shown and acting in the correct directions there. Boxes remain in contact with the belt, so the normals are still the same expression. Put everything together, substitute in, calculate the acceleration, and you have a higher acceleration for B than you do for A. Finally, we go to the kinematics problem. And the kinematics problem in this case was an equilateral triangle over here, which is attached to two links, which are OA and DB. In addition to that, you're given these distances CD, which is 0.2 meters, and OC, which is 0.2 meters. Equilateral triangular plate is controlled by the link AO and link DB. During the plane motions of link A or plate ABE, the two links cross but do not touch each other. So that's important to recognize. For the instance shown in the figure, the two links are rotating vertical to each other. Plate is rotating counterclockwise. So you know the direction, and that's what it's there at WABE of 2 rads per second. So here I have something that's going to tell me something about the velocity. Determine the angular velocity of link BD, determine the angular velocity of link AO, determine the relative velocity of E with respect to B in the XY coordinate system. So you have all of this. You have these distances here, which are given to you, 0.2 meters for OCOD, OC and CD. You have BD and BC, or AO, which are given as 0.6 meters and 0.5 meters. Determine, okay, so all of the coordinate directions are given, and we can start doing some things. Now, in this diagram, you'll notice that I have immediately placed in it a direction for the velocities. VB is acting in this direction, and VA is acting in this direction, and that's where I expect everything to go. And it's going to act normal to the link BD and the normal to the link OA. So I know that it's either X or Y dependent, so VB is going to be vertical, VA is going to be horizontal. I can define an angle alpha in there, and I can have all of the rest of the terms, and I just need to calculate all of the terms that remain. From right triangles, we get BE equals AB, which is equal to 0.5 meters. So we are given 0.3, 0.4 meters. It's a 3, 4, 5 triangle. Omega AB equals omega CB, which equals omega CA. Which equals 2 rads per second. Velocity of B is equal to 0.6 meters per second. Omega BD then is equal to 1.2 rads per second counterclockwise. So counterclockwise makes sense. Vertical upward makes sense. And there we go. VA, the other one, same thing. We now have all the terms we need. Calculate it. It's a little bit different length, and we get 1.33 meters. So it's a little bit longer than the other. Finally, velocity of E with respect to B is really going to be omega AB crossed with our E with respect to B. And we have all the terms there. RBE with respect to B is the distance BE cos theta I and BE sine theta j, and substitute in all the terms. Theta equals pi minus 3 minus alpha. Sine of alpha is 0.4 over 0.5. Substitute in all the terms, and you get this value of 0.92 on the I, 0.4 meters or j in the meters per second for velocity of E relative to B. So if you do this, you can also do it as a vector solution, and it's actually a little bit easier, I think, in the end. And substitute on all the terms, you have everything there. put in everything that you know, velocity of B, velocity of A, how to sort of break them up, set them all equal, and you get right away omega BD and omega AO, which is 1.2 rats per second, 1.33 rats per second in the K direction. And in both cases, or in one equation, you get out the whole solution. Again, my preference would be to solve it this way. I just find it easier. Velocity of EB, you just, again, cross terms out. Everything works, same as before. All right, so in this particular set of problems, we're sort of looking at the dynamic concept inventory, and I'll talk about it more explicitly in the final exam because there's more to it, but we're starting to deal with some of the rigid body components of that. Angular momentum is also something that honestly is one of the harder concepts in the course. We don't spend a lot of time on it. It's usually 2 lectures. And after that, we move on. So you do have to spend a lot of time to really think about it and really sort of, if you can, go back over the lecture and the lecture notes on that particular concept. Particle kinetics, rigid body kinematics is really where everything went with this. So as much as possible, try to look at these exams from that perspective. Thank you very much, and I'll talk with you later.